Hi again. We're now going to move on to learning objective 5.4 on applying the central limit theorem. So in order to understand how sampling distribution can lead to the central limit theorem, I want you to work on an activity. So I really do want you to do this activity individually, and then I'm going to come back to the spreadsheet here to summarize the conclusions from the activity only. So you do need to complete the activity individually. What you're going to do is you're going to open up this link and it will bring you to the activity. You can continue without signing in. You don't have to make an account. And then you can put in your name and you'll see the activity. So the first thing is we're going to be talking about candies in this activity, one of my personal favorites, which is Smarties. And in a box of Smarties, which is chocolate covered in a candy coating, there are 8 colors of Smarties. In most boxes of Smarties, there's around 40 candies. So if you had a box of 40, how many would you expect of each color? You'll type in your answer here, press share with the class, and then you'll be able to go to the next page. So according to Nestle, I actually did send them a message and they said that they try to have the exact same number of each color. So there should be the same amount in a box. But if you had your own box and I had my own box, would you expect us to actually have the same number of each candy? You'll say yes or no and then explain why. So I actually got a real box of Smarties and I had 7 out of 40 that were orange. Because you're online and I can't actually give you a box of Smarties in all of your different locations through the web, we're going to use a simulator to pretend we have Smarties. So you'll click on the link here and I'll show you how to use the simulator. So the first thing you're going to do is you're going to pretend you have a Halloween size of Smarties candies, which are only 10 in a box. For the Halloween size of Smarties, you're going to change the probability of orange to 1 in 8, since there are 8 colors of Smarties. The number of candies to only 10, and the number of samples to 1. Then, you'll switch it over to proportion of orange instead of number of orange, so you get a percent. And press Draw Sample. For my random sample, I only got 1 out of 10 orange. You might have got the same, you might have got 2, you might have got 0. It is random, so you might get a different amount. What you'll do is you'll enter your result here. And there's 10%, one person got it, that's me. As more people add their results, you'll see more dots appearing. Then you'll go to the next page, but you're going to pretend you have a regular size box that has 40 Smarties in it. I'm going to reset, change the number of candies to 40, and now see how many orange I might get. At 20% orange in 40 candies. So I'm going to type in 20%, share with class. There's my 20%. One person got it. That's me. Other people's numbers will show up here as more people complete the activity. Now you're going to pretend you have 1,000 candies, way more than we would have in a box, or we'd have to buy so many boxes to have 1,000 candies worth of Smarties. So I put in my 1,000. I'm going to reset. So I'm starting from scratch. And again, if you press hide candy machine, it will make it a bit faster. Otherwise, it might take a very long time. And I finally got about 10.4% orange in 1,000. You might have a slightly different answer. I want you to type in whatever you got here. Whoops, there we go. And again, share with class. Everybody's numbers will show up here. What I want you to do is as we increase the number of candies, I got 10, then I got 20, then I got 10.4. Do you notice any kind of pattern? I just want you to type in your observations in this box. Again, there's not really any wrong answers, just what do you see? Then we're going to actually move on to make this a little bit more precise. You're going to change the sample size and the number of samples. So instead of just doing one sample, you're going to do 1,000. So if we have 10 candies and we take 1,000 samples. That's kind of like when we did 3 students selected 3 times, but now instead of doing it 3 times, we're doing it 1,000 times. So select 10 candies 1,000 times. You'll need to turn on this box for summary statistic and it will show you the average value that you get. If I press draw sample, my average was 0.126. My standard deviation is about 0.109. So what you'll do is you'll type in that mean, that standard deviation, and you'll also have to try to describe the shape of this. Maybe you think it looks exponential, maybe you think it looks uniform. I think mine looks closer to almost an exponential distribution. Then you'll do the same thing, but instead of for size Halloween size, you'll do regular box size of Smarties, 40 of them with 1,000 samples. That pretends you have 1,000 boxes of Smarties. I got a mean of 0.127, standard deviation of 0.052. So you type that in and you describe the shape. What do you think this shape looks like? Then you would finally do it one more time. 1,000 candies, 1,000 samples. Might take a while for this one because you have so many, but once you get your mean, your standard deviation, and your picture, you're going to describe the shape, and then you're going to enter the exact numbers for the mean and standard deviation. So for example, I got 0.125, 0.011, and I put what I think the shape looks like. Okay. The final thing is you want to try to summarize your findings. As the sample size increases, what is happening to the shape of the distribution? So by that, I mean when you moved from only 10 candies to 40 to 1,000, what happened to the shape? Pick which option makes the most sense. It will tell you if you've chosen the right one when you press submit. As the sample size increases, what happens to the mean? Tell me what you think happens. You'll get the check when you press the select one. And again, what happens to the standard deviation? Choose which one you think makes the most sense based on the 3 values you filled in to your tables for the standard deviation. Then, as a last part of this activity, we're going to go back into Excel and you're going to look at this pattern for numbers instead of just for a proportion of orange, which is a percentage. We're going to actually do this for an average or a mean with dice. So at this point, you'll have to go back to Excel and click on the dice activity sheet. What you're going to do is use rand between to pretend you're rolling a die. For a die, there's 6 sides, so the rand between should be between 1 and 6. Then you're going to drag this down to pretend that you rolled the die 1,000 times. So you're going to fill it in until you have 1,000 random rolls of the die. For the 1,000 random rolls, you're going to make a histogram. The histogram might look a bit weird just because of the bin width Excel chooses. If you force it to only have 6 bins, one for each number on the die, it will look better because there's 6 possible numbers, 6 bins. So this is for one die. If you want, you could try to make it look more pretty. I'm just going to get rid of some of the background there. And then I also want you to find the average of the rolls. So when I roll one die, I get an average of 3.444 and find the standard deviation. This is a sample of 1,000. So I'll use .s and that's my standard deviation. Then you're going to do this for 2 die. So if this is 1, I'm actually just going to copy paste to speed this up a little bit. I'm going to paste the random numbers for 2 possible die. And then instead of focusing just on the rolls, I'm going to look at the average of the rolls. So the average of the rolls, and this time I'm going to make a histogram of the average of 2 rolls. I'm going to first insert a histogram. Again, you can make it look prettier. Then you need to find the average, not of the rolls, but the average of the average. and the standard deviation of the average. Then I want you to do this again for however many die you want. So it has to be more than two. You could do three, you could do four, you could do five, and then find the average of however many dice you do. Make a histogram of the average, the mean of the average, and the standard deviation of the average. Once you've done that, come back to the activity and summarize in the box what happens to the shape, what happens to the mean, what happens to the standard deviation. What do you notice happens in each of those scenarios as you're making the histogram, as you're finding the mean, and as you're finding the standard deviation? What is happening? Okay. So the last thing is I want you to just tell me if you had any issues with the activity, how you're feeling. Did you think it was interesting and made sense? Then you put your point here. If you thought it made sense but it wasn't interesting, maybe you put it somewhere down here. If you didn't find it interesting and you were confused, you put it in here. If you found it interesting but a little bit confusing, maybe you put it in here. If you have questions, you type them in the box for me here, and only I will be able to see them, not your classmates. And that will be it. You'll be done the activity after that point. After you're done the activity, you'll come back into Excel, and I'm going to explain the results of the activity. So if you didn't actually do the activity, please pause the video here, and I need you to actually try the activity. Once you actually try it, you'll see the results yourself, and it will make the central limit theorem way more clear if you do the activity. So the activity has three key takeaways that show you the central limit theorem. First, as you increase your sample size, the shape of the distribution should look more like the normal distribution. Did you see that with your simulation? Did it look more like the normal distribution as you changed the number of candies and increased them? This does look like a normal distribution for 1,000 candies. For 40 candies, it kind of looked like a normal distribution, but with some far spaced bars. And for only 10 candies, it didn't really look like a normal distribution. It looked more exponential. So as you increase, it should look more like a normal distribution. Also, what happens to the average as you increase? If I look at my averages, add 0.126, 0.127, and then 0.125. It should get closer to the probability in theory, which is 1 in 8, since there's 8 colors of Smarties. So as you increase the sample size, it should, in theory, get closer to that theoretical proportion of oranges. Finally, what about the standard deviation? It was about 10.1, 10%. Then it was about 5%. Then it was about 1%. The standard deviation should get smaller as you increase the sample size. This happens with both the proportion for oranges and for the dice activity as well. If you did the dice activity, and let's say you did 4 different dice, and then you found the average of 4 rolls, let's say, and whoops, did I do that for the whole column? Yeah, I just selected the wrong data. Did the column instead of the row. You want the average of the row. And then I make my little picture, my sampling distribution. This is what a sampling distribution is, a histogram of the average. This is my sampling distribution for 4 different die being rolled. The mean of 4 different die being rolled is that number, and the standard deviation is this number. So with 1 die, the distribution looked more or less uniform. The mean was close to 3.5 and the standard deviation was about 1.67. When we move to the average of 2 die, the mean is still close to 1.5, but the standard deviation is now 1.24, and the histogram kind of looks like a triangle. They call that a triangular distribution. When we increase the number of rolls to 4, die 4, it looks more like a normal distribution, that it's quite symmetric in this case. The mean is still about 3.5, but the standard deviation is about zero point 0.8. So those three rules are still true, that the shape should look more normal. The mean gets closer to the real value. Remember when you roll a die, that the mean or average expected value should be 3.5. So we get close to 3.5 for the mean, and the standard deviation gets smaller from 1.7 to 1.2 to 0.8. And that will always happen as you increase the sample size. This leads to what's called the central limit theorem. What the central limit theorem says is that no matter what distribution you start with, so even if when you roll one die, you start with a uniform distribution, or when you look at the Smarties, maybe you start with more of an exponential distribution. It doesn't matter what distribution you start with. As long as you have a large enough sample size, you're going to end up with a normal distribution when you focus on the sample mean or the sample proportion. So what I mean by that is instead of focusing on the individual values, if you average them, or like for the Smarties, if you find a percent of orange and find that percentage, then when you focus on what you calculated, the average over many samples or the percent over many samples, you're going to get a normal distribution. Why this is helpful is then you can use the normal distribution function in Excel to find probabilities, like norm dist, standardize, or the norm inv function to find values based on probabilities. And we actually have formulas we can use that for proportions, they will follow a normal distribution. When you focus on the probabilities of success, the proportion, where the mean of the distribution is P, the population proportion, like that in theory, we think there's 1 in 8 oranges, for example, and the standard deviation will follow the formula P times 1 minus P over N square rooted. Because it's divided by N, the sample size, that's why the standard deviation always gets smaller the bigger your sample size gets. There's also a version for the mean that when you have a mean value, the average of the distribution is the theoretical mean mu, and the standard deviation is sigma, the standard deviation, over root n. Because again, you're dividing by n, that's why it gets smaller the bigger the sample you take. Because if you're dividing by a bigger value, your number is going to get smaller and smaller and smaller. So why does it make sense that even if you start with some weird distribution like this weird curve, or if you start with a uniform distribution like for the dice, why do you end up with a normal distribution? Why does that make sense? The idea is that when you focus on a mean or a proportion from a sample, it's going to be a lot harder to get an unusual observation. What that means is, imagine we were talking about heights. Would it be that unusual to find someone at Cambrian that's like 6'6"? No, I can find one student that's that tall. But what if I went to every single class at Cambrian and I took an average of the heights in the class? Do you think I'm going to find a class where the average height of all students is 6'6"? No. So when you're focused on one person, it's easy to get an outlier or an unusual value. But when you're focused on the average, like of a whole class of students, most of the average heights in a classroom will be around the average height of people in Canada. It won't be super, super tall, like 6'6", or super, super short, like only 4'11". So because of that relationship, most of the values end up being in the middle, and you get very, very few values that are really high and really low, and that creates the normal distribution shape, like we have here or here. It will change every time slightly when I run it because it's different random values, but it will create that normal distribution shape. What's the cool thing about this, and what is this is actually one of the most important theorems in statistics, is because you end up with that normal shape, That means you don't even really need to know about the original weird distribution because we know so much about the normal distribution and we can calculate the probabilities in Excel. We're going to be able to find probabilities as long as your sample size is large enough. And what's cool again about doing it in the activity format is you can see that normal shape appear yourself, even when you start with uniform distribution, or for the dice activity, if you start with one that looks more like exponential, like a triangle, something like that, when you increase the sample size, you will start to see that normal distribution shape appear. You see that the mean gets closer to that 1.25, or for the dice, it gets closer to that 3.5, and you should see that the standard deviation gets smaller. And that's the central limit theorem. If you have any questions about the central limit theorem, please feel free to reach out because it is one of our most important concepts in the course. Thank you. I hope you enjoyed the activity.